assistant professor at the National Center for Nuclear Research in Warsaw. Her research is focused on astrophysical dust and chemical enrichment of the galaxies. She holds a PhD from the CISA in Trieste, and she had various postdoctoral fellowships in UK, in Italy, and France. And now, since 3 years, I think, or 4, she gave a competitive grant in Poland. And she's also part of numerous global collaborations, LSST and ZGAL teams. So today, Ambra will present a talk with a title, Forging Cosmic Dust, the role of thermally pulsing AGB stars. So Ambra, we can start. You have 45 minutes, and I will award you 5 minutes.
Okay. Thank you very much. Thanks for this invitation. It's a real pleasure to be here today. So my talk, as the title says, is focused on dust in the universe, and in particular the role of thermally pulsing asymptotic giant branch stars that are represented the last phases of low and intermediate mass stars. During this phase, the star loses it's okay, the pointer doesn't show that, but basically from this image from ALMA, we clearly see in our galaxies that the star is losing mass at high rates, and this image shows us the gas that the central star is losing, and this also traces the dust of the star. Why studying dust is important? So dust is composed by small solid particles of few hundreds of microns up to few microns. It can be composed by silicates or carbonaceous material. In case of silicates, we have that the composition, the compound is made of magnesium, silicon, and oxygen, and otherwise we have carbon material. Dust is formed, therefore, from metals forged in stars, and is about 1% of the total mass of the baryons in the universe. So we might think that this component is negligible for our understanding of the astrophysics of different objects, but nevertheless, this is not true, because dust is important in several astrophysical contexts, such the gas in molecular clouds from the radiation, so the gas can cool down and we can favor star formation. We have a molecule formation on the top of dust grains, because these dust grains can act as mechanical catalyst for the formation of molecules. On the surface, we can collect atoms and molecules that form larger compounds, up to also organic molecules. We have that the dust is the first step to form planets, and also we can study our own solar system through the presolar grains formed from mostly from TP-AGB stars. Also, dust is very important in stellar evolution, because in the last phases of low and intermediate mass stars, we have that the formation of dust helps the process of mass loss, so favoring the enrichment of the interstellar medium. And also dust is very important in the baryon cycle of galaxies overall. In particular, we have that in galaxies, dust is absorbing the UV, mostly the UV and visible lights from stars, as we can see in the Milky Way in the top panel. So we have that the dark areas are areas in which the stellar light is attenuated by the presence of dust, and this energy is re-emitted in the infrared bands. And basically, if we have galaxies in which the stars are not resolved, we have that the integrated light of our stellar population is reduced by dust attenuation. So we go from the blue emission to the green emission, and the energy is absorbed, is re-emitted in the infrared bands. So dust really shapes the spectral energy distribution of galaxies, and we have to study dust in order to understand the physical properties of galaxies, such as their stellar content, their baryon content, and star formation rates. We see dust through different facilities. So we had Spitzer and Herschel in the mid and far infrared bands. For high redshift objects, we have to go with ALMA and NOEMA arrays. And recently, of course, we have the James Webb that allows us to study dust up to about 2 gigayears after the Big Bang, in particular polycyclic aromatic hydrocarbons that are building blocks of dust, but also stellar population and stars in galaxies 500 gigayears after the Big Bang. So dust is not a component that is static, but evolves with time. So of course, we have the contribution to the enrichment of the interstellar medium from low intermediate massive stars at the end of their evolution. So during the TP-AGB phase. First, to be honest, we have dust from type 2 supernova, so from massive stars that has a shorter time scale of evolution, and followed by the TP-AGB stars. This dust and metals that is produced in the stellar interior is released in the interstellar medium and is reprocessed. And at the end, we have that these metals are going to form new stars. So dust during this process can be destroyed by supernova shocks or grow, can be accreted also in the dense phase of the interstellar medium. And we have also large-scale processes such as inflows and outflows of material. So it's a very complex scenario. And in this scenario, thermally pulsing asymptotic giant branch stars can account for about half of the dust in the local universe, so are not negligible objects, and may be important also at high redshift, even though their role is still debated, and we'll tell you something toward the end of this talk. And thermally pulsing asymptotic giant branch stars cannot be neglected also because most of the stars will go through this phase. So the elements in the universe are produced by different sources. This is a periodic table that shows which elements are produced from in the local universe from different sources, different channels, and we have that depending on which metals we have a different kind of dust. So as I was mentioning, silicates are formed by magnesium, silicon, and oxygen. And this material comes from mostly from exploding massive stars. And so we can think that at the beginning in our solar system, we have silicates, but then we have that the carbon instead is produced mostly by low and intermediate massive stars. And therefore, the nature of dust changes with time, and this has important consequences for modeling the emission of dust. Iron comes from type 1A supernova mostly, and we have other heavy elements also from low and intermediate massive stars and neutron stars merger. So we have a very dynamic scenario, but how these TP-AGB stars can produce carbon. So normally we have that these stars has carbon over oxygen ratio below 1, but due to the fact that these stars have the third Rejap episodes, we can switch from oxygen-rich star to a carbon-rich star. The star is losing mass at high rates, and we can have also, so this process, the third Rejap is for, depends on the metallicity, so the lower is the metallicity, the more efficient tend to be the Rejap, and also we have that it's more efficient, is efficient, it occurs for stellar masses above around 2 solar masses. And for more massive AGB stars of mass above 4 solar masses, we can have also the hot bottom burning. So we can have that a carbon-rich stars can be converted in an oxygen-rich star due to the fact that we have the CN cycle activated, and so we are decreasing the amount of carbon in the atmosphere. But why this carbon C/O ratio is so important? Basically because when we switch from an oxygen-rich to a carbon-rich star, we change the composition of the stellar surface and on the molecules and dust that we form. And this is because in the case the C over O ratio is less than 1, we have that all the carbon available is locked in the very stable CO molecules. So these molecules is not is very stable and is not involved in the process of forming dust. So we have an excess of oxygen in the atmosphere available to form molecules such as water, silicon oxides, and dust. On the other hand, if the C over O ratio is greater than 1, we have that all the oxygen is locked in the CO molecules. So we have an excess of carbon available to form molecules which are carbon-based, such as, for example, acetylene, which are the building blocks for the formation of carbonaceous material. This is a schematic representation of a circumstellar envelope of a TP-AGB stars. So we have we have a pulsation from the atmosphere of these stars, and we have that this pulsation helps the process of dust formation and of mass loss. In particular, we have that these pulsations are lifting the material up to a zone in which the temperature is low enough to allow the condensation of dust, because otherwise dust evaporates due to the stellar radiation that makes dust reach a very high temperature, the sublimation temperature. And we have the two cases, so the oxygen rich and the carbon rich case. In one case, we form mostly silicates and oxides. In the other case, we form carbonaceous material. And what is important is that when dust is formed, we can have the so-called dust-driven wind, which basically means if we look at this equation at the top, this is the acceleration equation, and it tells us when we can have a dust-driven wind, which means that basically the photons coming from the photosphere are impinging on the green surface and are transferring momentum. And if the momentum can overcome the pull of the star from gravitation, we can have this wind. And this depends on the parameter gamma. And gamma is depending on the stellar parameters and on the opacity of the medium. Dust is very opaque, more than gas. And when dust is formed, we have that the opacity is enhanced. And as a consequence, this gamma parameter can become greater than 1, and we can have that the outflow is accelerated. And this also helps the process of mass loss of the star. And the one important observable related to this is the expansion velocity that can be measured, for example, from CO lines or from OH maser emission for massive oxygen-rich stars. So this is still the schematic representation, and on the right I put this panel that has the gas temperature versus the gas pressure. And in particular, the different lines that we see, different black lines, represent where dust can condense, where different dust species can condense. This is the case for oxygen-rich star. So above each line, we are not able to form dust. Below each line, we can form dust. So we are in the favorable condition to form dust on the chemical point of view, but also on the physical point of view, because the stellar radiation is not so hard to eat up the dust grains and make them sublimate. And so different kind of dust are formed in different part of the circumstellar envelope. Corundum is the first one to form in oxygen-rich stars. And basically, the red line represents a model of the circumstellar envelope. So we are going from high temperature to lower temperature as we move from the top to the bottom. And here it means that we are moving from the stellar atmosphere outwards. And in this case, when we form silicates, we have the dust-driven wind. So not all the species can actually be able to trigger this dust-driven wind, but only the more opaque ones and the more abundant ones. In case of oxygen-rich, it's believed that silicates are the driving for the mass loss and wind. In case of C-rich stars, it's believed to be the amorphous carbon dust. And the models that I used during my studies is basically the stationary wind model that takes as input the stellar parameters such as the current stellar mass, effective temperature, stellar luminosity. We have to assume the mass loss, so it's not predicted. And this comes also can come also from stellar evolutionary model. If we want to apply our model to stellar tracks, this is possible, and elements abundance at the surface of the star, in particular the silver ratio. As output, we have the dust mass, dust composition, outflow velocity, and we can also compute the spectra because we have additive transfer calculation. And we can compare this output with the observations, and in particular, we can estimate the dust yields produced during the entire duration of the AGB phase. We can put some constraints about dust growth and destruction mechanisms, also about grain size and optical properties of dust, and we can estimate through the LCD fitting the dust production if we have the LCD of resolved stars, and this I will show you later. So for different kind of spectral types, so oxygen-rich type, we have a feature from silicate and aluminum oxide, for example, and we have that these features are changing with the evolutionary state of the star. So for stars that are not that evolve, we have that we see the corundum feature, but as the star evolves, it produces more silicates, and so the corundum feature disappears and is overcome by the silicate feature. And this gives us hints about how dust is formed and in which abundance is formed as a function of the stellar parameters. So the dust produced in oxygen-rich types is linked to the initial metallicity of the star. So the more metal-rich, the more dust we form. And this is a consequence for the dust-driven wind. In particular, we see this in the expansion velocity of the stars. So here we have expansion velocity versus pulsation period. And we see basically two classes of expansion velocity. So for the galaxy, which has higher metallicity, and for the large Magellanic Cloud, which is characterized by metallicity about half solar. And so we see that since for these stars, the dust production, the production of silicates is connected to the metallicity. As the metallicity decreases, the expansion velocity is lower, as we can expect. So this is for oxygen-rich stars, and what drives the wind of these stars. As I was mentioning, we believe it's silicates, but also there is a debate about the composition of these silicates, if it's iron-rich or iron-free, for example. There is, from hydrodynamical simulation, people have studied the iron-free case, in which the wind is driven by large iron-free grains through scattering. If we are in the iron-rich case, we have both scattering and absorption. And in this case, here you see the expansion velocity versus the mass loss rate. So the black points are observation in our galaxies, and these are different initial stellar masses. These are simulation of our dust group code coupled with the stellar tracks. And so we see that also in this case, we have that the observations are well reproduced by our framework. For carbon-rich stars, we have amorphous carbon that is featureless, and it's important to notice that the abundance of carbon around the carbon-rich stars is not directly linked on the initial metallicity. And this is because we have the dredge-up episodes, and as a consequence, the amount of carbon can be very abundant, and we can form a lot of amorphous carbon dust. On the other hand, silicon carbide is limited by the amount of silicon in the initially available in the star, as well as also magnesium sulfide. And for these two species, we have a feature at 11.3 micron and a bump around 30 microns respectively. And people have been studied how this feature changes with the stellar properties, in particular with the mass loss and the metallicity. And so here we have the Spitzer spectrum, and people have been studying the SAC feature strengths as a function of essentially of the dust produced. And this method basically takes the feature strengths and as a function of this color, which is 6.4 minus 9.3 microns. And in these bands, basically, we are not affected by molecular features. So that's why this color is used. And this plot tells us that basically at a given mass loss rate, essentially, we have that as we increase the metallicity from the metallicity of the Small Magellanic Cloud to the Milky Way metallicity, we have that the feature strength increases. And this is likely due to the fact that we increase the amount of silicon carbide because the metallicity is increasing. And the same, similar is for the magnesium sulfide. So the production of this species is delayed for low metallicity case, as we can see in the Small Magellanic Cloud. And so this feature is more prominent at higher metallicity. As I said, carbon dust is the driver of dust-driven wind for carbon-rich stars. So we expect that we might expect that this the expansion velocity in the circumstellar envelope of carbon-rich stars is not related to the metallicity. We don't have many data, but here if we look at the expansion velocity versus the period for galactic and LMC case, it seems that there is actually a trend with the metallicity as well. This can be counterintuitive in the sense that if you look at this, for example, at hydrodynamical simulation, we see that for a given mass loss rate, as we increase the carbon excess, we increase the wind speed. And this is logical because if we increase the carbon excess, means that we are forming more carbon dust. But it's also true that we tend to have a higher carbon excess if we decrease the metallicity. So in the observation, we should somehow expect the contrary than what we see. So we should expect that the expansion velocity increases for decreasing metallicity because we have more carbon. The dredge up is more efficient. So this seems counterintuitive, but actually there is a reason why. And one possible interpretation is can be derived from looking at our Dastro model coupled with the stellar tracks. And in particular, if we apply our model to stellar tracks, we have that our dust growth and wind speed changes with all the stellar parameters, not just with the carbon axis. And so we see that so here we have the wind speed as a function of the luminosity, and here we have decreasing metallicities as I move in this direction, right here. So solar metallicity, LMC, SMC, and galactic halo. We see that for stellar masses below or equal to solar masses, we tend to have actually that the predicted expansion velocity increases with decreasing metallicity. And this is because the carbon excess, the dredge up is really dominant in determining the amount of carbon form and therefore the wind speed. And so this is what is in line with what is found from hydrodynamical simulation. But what is interesting is to look at the three solar masses, because as we move to lower metallicity, we actually find that the expansion velocity tends to decrease with the metallicity. And this is because we still have the effect of the dredge up for these stars. We have a lot of carbon in the surface, but at the same time, we have that these stars is becoming hotter and hotter. And as a consequence, dust is not favored in its formation, and the wind speed tends to decrease. So in this case, we see something that is more aligned with observation. So this is just to say that we have to look overall to the evolution of the star coupled with our dust growth to really understand what's going on for carbon-rich stars. But as I said, also there are not many observations. Now we have an approved ALMA proposal, so we are waiting for data to be reduced, and so we can maybe tell more about this in a few months. Okay, we also can put the constraints on the models from pre-solar grains by matching the dust flow scheme with the stellar tracks, and in particular this is done for metallicity around solar. In this case, we coupled, also in the previous case, actually, we coupled the dust-growing wind dynamics with fruity evolutionary tracks by Sergio and the group. And basically, we find that we find a way to constrain the model in such a way that the size of silicon carbide grains can match, well match the what we find for pre-solar grains in meteorites. And so we find that the size distribution of these silicon carbide grains is fairly well reproduced by stars around 2 solar masses and metallicity around solar. So dust production from TP-AGB stars, and so how we can estimate how much dust a star that we see, for which we see the spectral energy distribution is forming dust in this moment. So basically we can do this through the SCD fitting. Here you see an example of SCD, observe SCD in red, and observe spectra in black, the thick lines. This is a Spitzer spectra. And basically the thin black line is the best fitting models, and the blue triangles are the photometry from the model that have been computed by integrating the, by convolving with the response curve of the filters. And basically, so this, we can estimate the dust production rate, so how much dust, the amount of dust per year that is being produced by the star through the SCD fitting and through this relation. And in particular, we have that this depends on the dust production rate depends on the optical depth that is fixed by the model and the fit, the expansion velocity that we assume or that we predict. In our case, we don't need to assume the expansion velocity because it's predicted by the model, and by the optical properties of dust. And for the mass loss rate, we just multiply the dust production rate for the gas to dust ratio. Many people assume this number, but with the model, we don't need to assume this number because it's directly predicted by the calculation. So when we do this radiative transfer modeling to fit the stars, there is a problem for, this is for carbon-rich stars, that we have several optical properties available in the literature, for example, for carbon grains. And if you change the optical properties, you really change the color and spectra of these stars. This is J minus K color as a function of the grain size for different optical data set available in the literature. So for a given optical, for a given grain size, we have that we have a larger variation in this color for different optical data sets. On the other hand, if we fix on one given optical data set, we have a larger variation as a function of the grain size. So how to do this? How we select these optical properties to do our calculation? Well, we can try to constrain these optical properties by comparing the model prediction with observations. And we did this. Basically, the left, this is, so we Basically, our aim was to simultaneously reproduce the most important color diagrams simultaneously in the near and mid-infrared from Chumas and Spitzer. Basically, this is an example in the left of a bad behaving case. So we have these color diagrams. We have that the red points are carbon stars in the small Magellanic Cloud. The green points are extreme stars. That means that they produce a lot of dust. So they are called extremes because they have extremely red colors. And most of them in the Magellanic Cloud are carbon rich. We have spectroscopic confirmation for a subsample of them. And these blue point are just the average of the observed one in different J minus K range. And the black lines are what we obtain by couple the Dasgro model with the stellar evolutionary tracks. In particular, we see that in these cases, for this combination of optical data set and grain sizes, the colors are not well reproduced, while in the right panel, we have that for this combination of optical properties and grain size, we can very well match the model with observations. And this happens if we have small grains that seems to best reproduce these color diagrams in the infrared. Of course, we have some assumption here that we have spherical grains and compact grains, but okay, this is what we get. And also we had some further constraints on Gaia data release 2, and a combination of Gaia data release 2 and Chumas colors. In particular, here we have K-band as a function of this function that is called Vesenite function. But okay, doesn't matter the details. Here, what is important to notice is that the points that are observation are color-coded with the J minus K, so they become redder as the J minus K increases, so the star is redder and redder is the color. And so as the star becomes redder and redder in J minus K, we have that the observation moves in this direction in this Vesenite function. But for the models, we find two different behaviors. So the black one is the models applied to stellar tracks. And we see that, for example, in this case, that was well behaving for the infrared colors. We have a totally wrong behavior for this plot here, while for other cases, we find a good match with the observations. And in the end, we tested around 50 combinations of optical data set and grain sizes, and only 2 combinations simultaneously reproduced the infrared observation and this kind of plot from Gaia data release 2. And so we constrain it in such a way that we have small grains and these 2 different optical data sets that I just mentioned, if someone is interested. Okay, so at this point, we can compute grids of spectra reprocessed by dust and perform systematically the SCD fitting for the carbon stars in the Magellanic Clouds. We fitted around 3,000 carbon stars for the small Magellanic Cloud and 8,000 for the large Magellanic Clouds. And we consistently computed the dust production rate, mass loss rate, gas to dust ratio, and dust composition. In particular, here are the inputs of the model. As I was mentioning before, we have the stellar parameters, and we have the optical data, the optical properties that have been constrained previously. And as output, we have the circumstellar envelope. We perform the SCD fitting, and we get this information here. And so when we compare with the literature our results, we find that actually by using this model and the well-constrained optical properties produces different results from the literature. So for the Large Magellanic Clouds, we are kind of in agreement with Ribel et al. 2012, for example, but actually the variation or the results can be of a factor 5 for the Small Magellanic Cloud or 3 for the Large Magellanic Cloud. So this is really depending on your assumption or your optical constant, and one has to be careful and use something that can really match the observation in order to perform this kind of estimates. So something about the very low metallicity galaxies. So if we look at the low metallicity universe, that can be representative of also the local counterparts of high redshift, we find something very interesting, because we have that the dust production rate from stars normalized by the stellar mass of the galaxies as a function of the metallicity seems to remain rather constant with the metallicity. And this is because these galaxies are star forming. And as a consequence, we believe that most of the stars present are carbon rich, so their dust production is not really dependent on the metallicity. This is different, for example, from low metallicity AGB stars in globular cluster that has a mass of around 1 solar masses. So in this case, we have only silicate production and low dust enrichment, because we have a low amount of silicates and other compounds in the circumstellar envelope. So this is something that is very new, and basically these are results, these are observation, a combination of ancillary observation of Sexton A, that is a galaxy that has 3% solar metallicity, so very, very low metallicity, and a combination of ancillary data and James Webb data. In particular, we have the MIRI spectra here. And so these are attempts to fit an oxygen-rich stars at this very low metallicity. And the problem that we have in these two fit is basically that no matter if we change the silicates optical properties, we have always this silicate feature here that is not seen in the spectrum. So how to solve this? Basically, what we found is that these stars are best fitted by a very small amount of silicates, around 1% if we assume that the silicates are enriched with iron, and 99% of pure iron, that is featureless. Or if we assume a different, that we have iron-free silicates, just 2% of iron-free silicates and 98% of iron dust. And this is very interesting because it means that at low metallicity, the formation of dust and the dust composition can be very different from AGB stars, can be very different from what we have at higher metallicity close to solar. And also to have the excess observed, we need a very high mass loss rate, which is also interesting because it's not really clear how we can get this very high mass loss rate in this scenario, in this low metallicity scenario. So this is something that needs to be investigated also by hydrodynamical models. And this is something for carbon-rich stars. Basically, we have here two cases. One case in which we have a less dusty stars, but that show the possible presence of silicon carbide. This is not 100% sure in the sense that we believe there is a silicon carbide here feature, but you see that the models, so the red are the models, the blue points are the data, and the black here points are the convolution of the model spectra with the filters. So here you see that there is a mismatch between these 2 points, the observed and theoretical. And here is believed that there might be some feature at this wavelength, absorption feature from acetylene. So it's something that we are still looking at. But what is interesting is that if we have a dust-producing star, actually this feature, this SIC feature disappears. And this we believe that might be related to the C/O ratio that is really increasing for stars that show a large amount of dust. So how we relate this information of TP-AGB stars in the context of dust evolution in galaxies? Well, we can perform a calculation of dust formation along the stellar tracks. So here we have the amount of the rate of dust produced as a function of time. And by integrating, we can derive this kind of plot. So we have the mass of dust as a function of the initial stellar mass for a given metallicity. And we can, here in red, we have the carbon dust, and in blue, the silicate dust. And we can actually study the dust composition as a function of the metallicity and the stellar mass. And we can use this information in codes that compute the evolution of dust in the interstellar medium of galaxies. So this is what I'm trying to do now. So studying, besides studying AGB stars, also studying the evolution of dust in the interstellar medium and of baryon evolution in general. And this is pretty interesting for high redshift objects observed with JWST. So with JWST, we were able to observe these galaxies at redshift 6.7. We have the rest frame optical and UV spectrum. And it's very interesting because in this spectrum, there is the signatures of polycyclic aromatic hydrocarbons that are based on carbon dust. And so how we have carbon dust at this very high redshift is not completely clear, because we expect carbon dust to be from AGB stars, but they might not be able to produce this carbon because their evolution timescale is quite slow. And this bump is pretty prominent if we compare, for example, with the one we have in the local universe is comparable to the LMC, for example. So this galaxy also has high dust extinction that is proved by H alpha over H beta ratio, and strong emission lines, oxygen lines, that are indicative of a fast metal enrichment in the interstellar medium. So we wanted to study this object, and basically these are the main results. Here is the observed spectrum in gray, and the predicted one from a consistent model of dust evolution in the interstellar medium and metal evolution, because we also have the lines. And on the right, you see how the dust evolves as a function of age. So we have different components. We have first that types of supernova are starting to reach the interstellar medium. Then we have that dust growth is kicking in and is contributing to the amount of dust in the interstellar medium. And finally, we have AGB stars. This is just for carbon dust. And actually, the black line is the amount of polycyclic aromatic hydrocarbons that we need in order to reproduce this feature here, this bump. So what we conclude from this is that AGB stars can be capable to produce some polycyclic aromatic hydrocarbons and eject it in the interstellar medium, but they are not enough. We need some other sources. For example, dust growth in the interstellar medium can be an option, but we are still working on that and trying to understand what's going on. And these are my conclusions. I leave it there, and thank you very much for your attention.
Ambra, also will be better time. Are there some questions? Oscar?
Oh, very interesting. Thank you. I have several questions for something that I have not understood. But related to the last part, mass loss is not predicted by stellar models.
No.
So you have to assume some mass loss rate.
Yes.
That is the calculations. So if you, I think how you can predict, you can make this predict this contribution to relative evolution of the dust content in the galaxy?
I have to assume the metal yields, basically. So
You have to assume
the metal yields. So I take the metal yields from the literature. And for example, in this case, I put myself in the most favorable condition to produce carbon from AGB stars. I took the yields from Portinari 98 that are not maybe the most updated, but was the case in which from preliminary calculation, I saw I had more carbon dust from AGB stars.
I have another one. So the second thing is concerned the pulsation, no? Because at a certain point you have mentioned that pulsation is related to this stuff, no? Because I understand that you have the muscles from the space of the star, and this material expands at a certain point, it's cool enough that dust can form, no? Then if you know how much mass is lost, and you can model the dust formation, you know how much dust is formed. And at the reverse, if you can measure how much dust it is formed, you can infer the mass loss.
Yes.
So that's the game.
Yes.
But how pulsation enter in this game? And where in the mass loss process or in the dust formation process?
In both, I would say in both cases, because, okay, it's not completely well understood. It's believed that the pulsation-driven mass loss is very important for low metallicity, because in that case, the dust is not, for oxygen-rich dust, for example, the dust is not abundant enough to have this dust-driven wind. So just from dust, it's not possible to have wind and to have mass loss. So for low metallicities for low mass loss rates also pulsation seems to have a big role. In the case of dust-driven wind, we have that the pulsation is important because it's allowing the material to reach a point in which the dust can condense, because otherwise it's sublimating. And at that point, we can form dust and we have the dust-driven wind. In my model specifically, I don't treat pulsation. So for this, you need hydrodynamical models. I just assume that, so if I don't have a dust-driven wind that is possible, can be produced, I just assume the dust to condense passively. So I just assume a certain expansion velocity, and this gives me the density from the stationary wind. Otherwise, I assume an initial expansion velocity, and then I follow the acceleration from the dust-driven wind. And I just assume that, let's say, the material reaches the point in which dust can condense. I have a version of this code in which actually I have an average shock profile that is can be important for the production of silicon carbide, for example, because it's before the onset of dust-driven wind, when we can assume it to have a stationary relation. But yes, I mean, it affects the condensation of these species, but on the other hand, there are many parameters entering, so it's not easy to calibrate these kind of models. But there is the possibility of having something approximate without hydrodynamics.
I asked it before because usually in the stellar models, the correlation between the mass loss and the pulsation period is used, but this is an empirical, purely empirical relationship. But the physical meanings of that is to be.
No, also to me. But no, the other approach is to use hydrodynamical calculation. At that point, one can model the pulsation and predict the mass loss rate. But the problem is that it's computationally costly. So it's difficult to apply consistently to large range of parameters and to do this kind of study, like statistical study with a large sample of stars like 3,000, 8,000. So for now is like a reasonable approach. I think the two approaches should be combined actually, so to have maybe the information from stationary winds and then people that can run more detailed simulations, taking maybe the inputs of stationary results.
Yeah, I have a question about this high redshift galaxies. If I understood, the problem is that you need carbon, but the time scale don't match with the AGB stars.
Yeah.
But this could be a problem similar to the appearance of Campbell stars in the heaven. So are you sure that AGB stars don't use this carbon?
No, no, I'm not sure about anything about this redshift. The thing is that it can be, okay, my hypothesis was to test if AGB stars can be a reasonable channel for this carbon production. And apparently, even if I put myself in the most favorable conditions, also in terms of star formation history, for example, yeah, I didn't go into much details about that. It seems that, I mean, in this case, I would need that all the carbon produced by AGB stars is in the form of polycyclic aromatic hydrocarbon. That is not the case. So this tells me that I need something else. So actually it can be Wolf-Rayet, it can be supernova, it can be dust growth. So it's still open field.
Question? How? Actually, is consider the observation of these stars. So, of course, the most of the usable information is at mid-5 elements. But I didn't understand if you are dealing with intrinsic emission only, or there is also a contribution from light scattered, light coming from the central star. And if so, if there is a role, what is the role of polarization?
Okay. So the role of polarization is something that is not very well studied in these AGB stars. When we have the, let's say, the final SCD, we have both the contribution from the stellar surface, and then we have the dust that, of course, is absorbing and scattering the light. For polarization, I think there is a couple of studies, but I should check them. Actually, it's not even clear if light is polarized, because this depends on if the grain is elongated or not. So it's something that I think is interesting to check, but at the moment, yeah.
I have a curiosity, but before my curiosity, I have a curiosity for Malo. Malo, vitality at the instrument we're going to be on top of galaxies. Does it have spectroscopic capabilities? Will it have?
Not at the moment,
But potentially
we could implement.
So would it be involved? These stars, especially very, they are very bright in the near, and we will have soon, probably facility that potentially could also do low resolution spectroscopy in the near infrared. How important it would be to have a grouping of nearby stars with low resolution? Because I know that sometimes we miss information. You said several times, so we're not having enough data. You yourself are mostly a modeler,
Yes.
and you compare your data with measurements, and measurements, you said sometimes they're missing. So how valuable would be this kind of information, or obviously probably quick, because we are limited to only try the stars?
I think it will be interesting to see the feature, the molecular feature in the near infrared, for example, to constrain the abundance of molecules. So one can, for example, relate the abundance of molecules with the abundance of dust and understand which can be the condensation fraction of this.
And that's something that possibly could be done with near inference spectroscopy.
Yeah, but you need a resolution of at least 5,000.
So with low resolution, you cannot really do much.
200. If you think that you can see, you can, yes, but describe the line of the slope. Usually depends on the source of guidance.
So now it starts,
No,
okay, there, the key band there, not there.
how much? They need to see numbers, so some J around 10, 12. So these are interesting numbers for low resolution spectroscopy. In the past, we had this we can cover with a low resolution, but at the resolution around 200. So at nearly equivalence. You can model the spectral energy distribution during model, also the low resolution. But unfortunately, as you see, most of the emission is in the medium, at longer wavelength. And so you need to go in Antarctica or in space. Yeah, yes, I think it's around 2.
Right, but they're very short. The point is that Google never needs to.
Let's say that for now,
Yeah.
if the star is not so dust enshrouded, it's interesting to relate like the molecules, the molecular content. I mean, I don't know the technicalities of the instrument, but of course, if you have a dust enshrouded stars, yes, in that case, you cannot just see anything, because everything is absorbed and re-emitted.
Such a large mass can be detected.
No, yes, if you have not so much dust, yes, but in that case, for example, yeah, is
Other question? If not, then we can thank again Ambra.
Yeah. And to spot which the cost in that's
Listen.